easy topics. So we start with electrical energy and power today. Energy and power. So what do we learn here? Electrical energy means the heating part of current. If you remember in grade 10 you have studied H is equal to I square RT, then power is equal to the product of voltage and current, P is equal to VI, P is equal to I square R. So same thing we will study. So let's say we have a conductor. You have a conductor out here, and this conductor is, say, this side is A and this side is B, and the current is flowing in this direction. Okay, just plain concepts. The current is flowing in this direction. It means that the potential at A has to be more than the potential at B. Then only the current will be flowing in this direction. And in time delta t, so in time delta t, how much what is the del q's value? Del q, charge, is equal to, current is always charge over time. So charge will be equal to the I current multiplied by delta t. Is this thing clear? Nothing great. These are all very simple. Okay. At this moment, if we see the change in potential energy, right? When the current is flowing, the current flows because this end is maintained at the higher potential, this end is maintained at the lower potential. So there will be a potential energy change. So we say the change is equal to V at A minus V at B, because A is maintained at a higher potential. So the potential energy lost by the charge. Why do we say potential energy lost by the charge? A charge at this side has a higher potential energy, and when it comes to this side, it has to lose its potential energy. Then only it is going to gain a kinetic energy and it's going to do its movement. So the loss is delta U is given by negative of delta Q V. Now, did you understand this? We used to say change in potential energy is always equals to negative of the work done, right? Negative of change in, the potential energy, potential difference. The potential difference is negative of the change in potential energy divided by Q. This is W by Q. That same formula we have used here. Okay. So now delta U becomes equals to how much? Just see, negative. Instead of delta Q, I'm putting I delta T into V, right? I delta T into V. So delta U can be said to be VI delta T. This is exactly your grade 10 definition, where you used to say that change in potential energy, you used to say power is equal to VI, energy is equal to VIT, if you remember. Right. So this means charge loses potential energy while moving from higher potential to lower potential. That's why it is negative. Anything difficult here? Clear? Okay. A question then arises, where does the energy go? Where does the energy go? You have lost energy. Where does the energy go? So there can be two choices here. Ideal case. Ideal means this will not happen actually. Ideal case means there is no collision for the charge as it travels through the conductor. There is no collision. So in this case, whatever potential energy the charge had, everything gets converted into kinetic energy. This is the ideal condition. But that is not the scenario. So what is the scenario? Whenever current goes through a conductor, you will always see there is a heat which is generated in the conductor. There is a heat which will be generated in the conductor, and that's called Joule's heating, which we will now see. Okay. So we say in a real conductor, our question is that of a real conductor, which you see in everyday life. So just write, in a real conductor, the electron will undergo collision and then it will undergo some more collision, right? And in this case, the energy gained by the electron is transferred to the atom. Did you understand? The electron is now behaving like a striker. So it is going on gaining energy, and it gains energy, and every time it gains energy, it is going to have a collision. It transfers its energy to the atom, results in the atom to vibrate. This atom will start to vibrate. And as it starts to vibrate, as the vibration goes up, this results in heat to go up. And this is what is known as Joule's heating. Electric current has got three effects: magnetic effect, heating effect, and chemical effect. Chemical effect is studied in chemistry, which is known as electrochemistry. Rest is Joule's heating. Joule's heating, if you remember grade 10, a current carrying wire develops a heat. Why does it develop a heat? Because as you apply current through the wire, there will be movement of charges. Ideal cases, all potential should have become kinetic energy, but the electron cannot gain complete kinetic energy. The electron undergoes collision. As it undergoes collision, it transfers its potential energy to the atom, the striking positive ion, and as a result, those atoms start vibrating. And as the atom starts to vibrate, the potential energy picks up. The heat energy picks up, and that is known as the Joule's heating. Okay, now let's discuss about Joule's heating also. Joule's heating. Joule's heating is simply, if you're grade 10, if you have a current I that is flowing through a conductor, and the conductor has a resistance of R, then the heat developed in the conductor is given by I square R into T for the time that the current flows through the conductor. That's why we always say, if you have high current devices like air conditioners and other things, your current wire rating should be very, very perfect, because temperature is not in your hand. Time is not in your hand. Resistance is not in your hand. The heat generated in a wire is proportional to square of the current. So this thing is also known as ohmic loss. You are losing energy due to heat, and this heat is of no use to it. So electrical energy is converted to heat energy. Now, there are two ways to see this. If you are having a heat appliance, then you use this principle. But if you are having a current carrying wire, where actually the wire is getting heated up, then in that case it is a loss. The heat is of no use to you. So all our heating devices will use this. Heating devices, for example, toasters, geysers, they'll all have an element, and in heating devices, we deliberately select material whose resistivity is very high. So more heat will be generated. Okay. So we call this as energy dissipated. Energy dissipated is always V into I into delta T. That is the time for which the current is going. And the unit will be Joule. Vi delta T. So here, can you define what is 1 joule of heat generated? 1 joule of heat is generated when a current of 1 ampere flows through a conductor for a time of 1 second, and the potential at the ends of the conductor is maintained at 1 volt. In that case, it will develop a heat which is equal to 1 joule. Okay, though whatever section we are going to study later, always remember, whether you are studying mechanical or electrical, power is always the rate of doing work. So power is work upon time, which is also same as energy upon time. So if you bring the time on this side, then it becomes power equal to Vi, which you used to do in grade 10. If you bring the time on this side, then it becomes energy by time, which gives you power, which is our next topic. Sorry, right? Our next topic is electrical power. But we will see power a lot in deeper when we do AC. Power is equal to delta W by delta T, which is also delta energy by delta T, because work is same as the amount of energy that you have in your body. So it becomes VI delta T divided by delta T. Delta T cancel. So power is equal to VI. In this case, we call this as unit as watt. 1 watt of power is generated when a conductor of current of 1 ampere flows through a conductor when its ends are maintained at a potential difference of 1 volt. So remember these formulas. Power equal to VI. Start playing Ohm's law here. Power is equal to I square R. Power equal to V square by R. And heat developed is power into time. Power into time. So this can be written as VI into T. It can be written as I square RT also. kWh, you remember? Kilowatt hour. Commercial unit of energy. You want to revisit? We can revisit. Though your course doesn't cover. Commercial unit of electricity is kilowatt hour. So let's see what is 1 kilowatt hour. 1 kilowatt hour is 1000 watts into R. That means 1000 into 1 joule per second into 3600 seconds. Seconds cut. So this is 3.6 into 10 to the power 6 joule. That is 1 kWh. And this is what people call in random language as unit. 1 unit of electricity. That 1 unit of electricity is 3.6 into 10 to the power 6 joules. So if your conductor, every conductor will have some sort of a resistance. So if you see it in this manner, a simple circuit, then there is a voltage, there is a current which is traveling, and there is a resistor. So we say this resistor is the one which gets heated up. So where does the heat come from? The resistor does not supply any heat. Heat is a form of energy. So you have, the cell has got chemical energy which gets converted to electrical energy, which further gets converted to heat energy. Right? Chalo. Our next topic will be power transmission. What are the care that we take in transmission of power? This much clear? Lot of formulas. Okay. Power is equal to VI. Power is energy per unit time. Power is energy per unit time. Some common sense before we get into our next topic. Just okay, let's see it like this. Which I keep on giving this example every time I have a mixer grinder. Okay, I have a mixer grinder. There are two mixer grinders with me. One is 2000 watts. One is 1500 watts. What do you understand by this? Get yourself clear. When you'll be buying from Amazon, you will see the mixer grinder written as 1500 watts, 2000 watts. What does this mean? In layman's language, when should you select what? Which one will you buy? Otherwise, what is the point in learning? What is the point in learning otherwise? Or let's take an example of a drill machine. I have a drill machine. Which is 2500 watts. I have a drill machine which is 1200 watts. What does it mean? Now, see, these are units of power. Clear? Power is equal to energy upon time. Can also be said as work done by time taken. Do you agree or not? Right? So let's take a drill machine. this is our drill machine. We have bought it from, say, Amazon, and it is stamped with 1200 watt and 2500 watt. Let's first understand what it means. The drill machine is going to take electrical energy from the power. It's a machine. It does not create its own energy. No one creates energy. Everyone converts energy. And a device which converts energy is an engine. This is a machine. Machine is any job, any item which makes your job much more easier. So machine is going to take up electrical energy, and finally the drill machine is going to rotate. So it's going to convert it into mechanical energy. Yes or no? In this process, you will also write a mail to the residents that a small drilling work is going on in our house. Kindly bear with us. Why? Because it is going to make noise. So there will be sound energy. You also expect the drill machine to get heated up. There will be heat energy. You also expect some sparks to be produced. So there will be some light energy. All these things are something which is lost in your process. Because if you are feeding him X, he's going to deliver X minus something only, right? That factor will be known as something called efficiency. Efficiency is output minus efficiency is the ratio of input, how many rotis you ate, how much work you are doing, divided by input into 100%. So let's say our drill machine is 98% efficient. That means if you feed it 100 joules, it will do work worth only 98 joules. 2 joules will go away this side. Is this thing understood? When Amazon sells you this at 2500, they can never measure what is the work output they will give. They will only measure what is these all things which are stamped are basically the input data. So while you drill this, when you run this drill machine, you are consuming 2500 joules per second. That is the cost on your pocket. Have you understood? This is the cost on your pocket. Based on that, it will do some sort of work. Well, definitely we can say how efficient the machine is. So sometimes when you want to host a disco party and you say, I've got 4800 watts. So you are, that 4800 watts means the energy it will consume is 4800 joules every second. You're going to pay for that, right? Now question arises, should I select this or should I select this? That depends upon what is your work criteria. If you are drilling a small hole, right, the amount of work you need is less. At that time, maybe this machine is sufficient to drill a hole. But say suppose I want to drill holes where I want to, put bolts to put up this screen. This is massive heavy. So at that time, if I use a 1200 watt drill machine, the machine will scream more. It will take longer time to do the work. It will take much longer. Finish will not be that good. And it will scream and yell a lot. Plus the drill bit, since heat will be developed more, the bit will wear out. So you need a heavy machine. A heavy machine will do the job in lesser amount of time. See, if it is consuming 2500 joules per second, considering losses, it will also deliver something like 2200 joules per second. Whereas this machine will be delivering something like 1000 joules per second. You're getting double the work, but be ready to pay also. But that pay gets compensated because you are using it for a much lesser time. So you use a mixer grinder, say suppose you are making a lot of everyday dosa batters and which are like, you want to make it absolutely with less water, proper grinding. I will go for a higher rated motor, but a higher rated motor will also pull in more electricity, but it will do a better job in lesser amount of time. That is what we know as power. Similarly, if you see an engine or a car will always have, see, if you see a car, right? In car, we have got 4 measurements. One is something called IHP, indicated horsepower. This is also power. This is how much the engine of the car is producing. Then definitely the car gets heated up. So there will be something called frictional horsepower. And finally, it will deliver something which is called brake horsepower, which every car dealer and all says so much BHP, 29 BHP. BHP is the brake horsepower, the horsepower available at the brakes or at the rotating wheel. So this is the conversion part. Okay, clear? Chalo. So now we go to something called power transmission. Power transmission. Power transmission means when you are transmitting electricity from one place to another place. When you go on highways, you will see big truss. You know what is a truss? all the poles or pylons that you see, and the wires which are, this is like interstate grid. Electricity is going from one city to the another city. Hundreds of thousands of kilometers electricity is actually being dissipated. Okay, not dissipated, transmitted. So in that case, again the question arises, I have got conductors. So the conductor will have something called I square RT. Now T is 24/7. The resistance of the conductor, I can't have a choice, right? So we will say that, sir, please select wires which are having less of resistance. Let's go silver. Pilferage will happen, right? So ideally it goes with copper or it goes with aluminum. Okay, aluminum is very good, but aluminum is very brittle. So in order to carry aluminum, you have to give another electrical iron wire as a guide. So aluminum becomes very costly. That's why whenever aluminum wires are sold, they say it's armored. Armored means along with the wire, another something will be going. So that's added cost. So copper is used. Now resistivity is not in your control. And 24/7. So don't you think the wires will get heated up? Yes, the wires will get heated up. And if the wires are getting heated up, then that is called transmission loss. Transmission and distribution loss. In the language of electricity generating companies, they call it, hey, this month our data is not good. TD losses are very high. TD means transmission distribution losses. So we'll see that now. Okay. Now, let's say power delivered to a city, power delivered to a city P is given as VI. We all know this formula. You are delivering this power, means you are transmitting. This is city A, okay, and the nearest grid, there is a grid. The grid is delivering this power to the city with traveling with some hundreds and thousands of kilometers. Okay, power delivered to the city, and the wires we are using, those wire resistance, let's say that is RC. So RC will be equal to V upon I as per Ohm's law. Okay, let's not put here directly. Okay, now power lost is PC, and lost power will be calculated as I square RC. Is this much clear? Power lost is I square RC. Now your question is how to reduce what you call PC. Your job is to bring this loss, because if you're transmitting, say, so many, how do we transmit power? We say so many gigawatts, so many megawatts. So many megawatts are being transmitted. I'm transmitting X, I'm not getting X because there is a loss in between, and that loss is given by I square RC. So you now need to remove this. Okay, so from here we can also say the power that you want to distribute is given by VI. So the current is given by P upon V. You can write it. The current is given by P upon V. Now power lost PC is equal to P square V square RC. Did you get this? Look, PC's value is I square. Instead of I square, we have put this. From this, we can infer that the loss of power is inversely proportional to the square of the voltage. This gives us a very nice indication. So what we do during transmission, the voltage is always jacked up. Voltage is jacked up. So when you I'll give you those ideas also. When you jack up the voltage, then what happens? The current will come down. For the same resistance, the current is going to come down. If the current comes down, then I square RC also comes down, which means the power also, PC also comes down. To do this, what grids will do? Grids will initially generate, say you are generating 240 volts AC. Then immediately they will feed it to a transformer. You remember transformer? a step up transformer, and then they will step it up to 133 kV. At 133 kilovolts, the electricity, that's why they are overhead going through at a huge height, they will be transmitted. And this transmission will happen, and then it will come to a city. And once it comes to city, you will always have something called substations. Like if you see our Pebble City, when at home we are using a voltage of how much? 240. Right near that security gate, there is a big transformer. 13 kV line is coming there. 13 kilovolts or 11 kV will come there. 11 kilovolts. You'll be fried. That 11 kilovolt is coming underground to your tower. And every tower has got an auto transformer which is converting it into 440. 440 step down to 240, and 240 is being fed in your house. Imagine railway trains. Trains are flying from one place to another place, which are like thousands of kilometers. So when a train is flying, the pantograph is actually touching the electric lines. These electric lines in our electricity lines are all 25 kV. If you touch, you're gone. So you can't. Now the question is the engine using at 25 kV? No, the engine will step it down. So whenever the railway engine comes, you will see a big noise making unit. That's the transformer that will step down that 25 kV. Ultimately, the lights that you switch on in your train compartments, those are only 25 volts DC. So they will convert AC, they'll convert AC to DC, step it down. But otherwise, long distance transmission becomes a huge issue. So in this section, what did we see? Power transmission. Power transmission is when you transmit electric power from one place to another place. When you're transmitting electric power from one place to another, there is a potential chance of power loss. And that is accounted in commercial language, we call that as TD losses, transmission distribution. So why that loss happens? The conductor which will be carrying that electrical signal will have a resistance 24/7. Time is not in your hands. And the power is now proportional to the current, square of the current. So your job is to reduce the current. How do you reduce the current? There is only one way. If you see Ohm's law, P is equal to VI, so or V by I is equal to R. So the only way you can reduce current is by jacking up the voltage. So our job will be to jack up the voltage. So power loss is equal to I square RC. I is again equal to V by I. So if you see, the power is directly related to inverse of the voltage. So increase the transmission voltage, reduce the power consumption between, not power consumption, power loss due to heat. Okay. So if you use high voltage for transmission, that is ideal. Otherwise, the wire will heat up very quickly. Fine. So this concludes power. At this section, some of the formulas that will be important for us are P is equal to VI, H is equal to I square RT, P is equal to I square R, then P is equal to V square by R, and power loss is always I square RC, whatever is. Chalo. Our next section is all about cells, EMF, and internal resistance. Cells, EMF, and internal resistance. Internal resistance. So let's just understand. Cell is something which always has chemical energy, which converts it into electrical energy, develops something called electromotive force. Electromotive force is a force which gives motive, that is motion, to whom? The charge carriers. So though we call it electromotive force, EMF is actually energy. EMF is not force. EMF is basically energy. That energy is used to give motion to the charge carriers. Okay. Now when the charge carriers inside that particular cell also move, they're not going to have a free pass. They will collide. And that collision develops a little bit of obstruction, which is an internal resistance. So let's understand like in plain language first, and then we'll proceed. This is a particular cell that I bought from the market, right? This is the plus side, this is the minus side. This will be stamped with 1.5 volts, which means open terminal voltage is 1.5 volts, right? So we say this is called the open terminal voltage. This V is equal to 1.5 volt. That means the maximum potential difference that can be maintained when you actually connect a circuit to it. When we connect a circuit to it, say whatever circuit is there, at that time it's 1.5 volts. But inside this cell also there will be some internal resistance. So actually this cell has an EMF of E, but you are getting V, right? The current that moves is the same current which is moving. That means if I see the internal resistance as small r, then IR is also voltage. This is called potential drop due to the internal resistance. So you are getting something which is V, and V will always be less, right? V will always be less. So if there was no internal resistance, electromotive force and potential terminal voltage should be same. But terminal voltage will always be less because the electron has to, like this is an obstruction, inside the cell also there is an obstruction. This is what we will study, and how this hampers our cell combinations. We will see that also. And this will give you an idea about, you do so much of power banks you use. So what happens in a power bank? We will see that too. So let's see the first section, which is known as the need or the necessity of cell. Why do you need a cell? So you can write down current flows as long as there is an electric field inside conductor. So if you have electric field inside conductor, current flows. This is known to us. So our next point will be, as electrons move, charges quickly neutralize. What do you mean by neutralize? They will be knocking off against positive ions and current would stop. It is very natural. You're moving and you are getting positive charges in between your root. You will neutralize with them and you will stop. So here comes your savior, which is known as a cell, or we can also use the word battery. What is a battery? A battery is a combination of cell. This is a cell, and this with again this with again this. This is known as a battery, and this is your cell. So this fellow will continuously, this will give a kick, will continuously separate the charges. Separate charges. How does it separate charge? By creating something more interesting out there, to which the charge gets attracted, and thus maintains a PD and maintains a PD, potential difference. So that's all why you need the cell. Okay. Next point is, let's see what is the structure of the cell. Structure. So a cell will have a positive electrode. A cell will have a negative electrode, and both these electrodes will be dipped in a electrolyte. A lot of this you have studied in grade 11 last year. But what I'll try to bring here into your understanding is, though this is electrochemistry, we have two types of cell, electrolytic and electrochemical. Get this concept clear for today, electrolytic and electrochemical. Up till grade 10, when you used to study about electroplating, electric refining, here input is electrical energy, output is chemical reaction. Here input is chemical reaction, output is electrical energy or electric current. Have you understood? Here we use the formula called don't panic. Don't panic means positive is anode, negative is cathode. Or we use the formula as I used to teach you all, Cartoon Network and Andhra Pradesh. Here it will be totally opposite. Here the positive will be cathode, the negative will be anode. Now this is kiddo way of learning. The proper way of learning is anode is the electrode at which oxidation happens, right? That is true for both. Anode is the electrode where oxidation will happen. If you remember in electrochemistry, oxidation used to happen at anode. Here also oxidation happens at anode. That's the only, this is the right definition. But if you see, don't write cathode as negative out here. Here cathode is positive. This is an electrochemical cell. This is an electrolytic cell. Here I supply electricity to get reaction. Here I do reaction to get electricity. So all your cells and other things, okay? Electrolyte, and this combination will do a chemical reaction which will maintain PD, So once the PD is no more maintained, means the chemical reaction has ceased. If you have a rechargeable cell, like your mobile batteries and all, they're very stylish. When you charge them, they behave as electrolytic cell because you're supplying now electricity and you are reversing the chemical reaction. Once it is charged, you plug out the electricity and now the chemical reaction is going to give the electricity. So the first type of rechargeable cells were called NiCd, nickel cadmium. When we were at your age, nickel cadmium cells were used a lot. Now nickel cadmium, now everything is lithium cells. So people use a lot of lithium cells. ठीक है? चलें आगे. So need, structure we have seen. Our third topic is EMF. These are all under cells. EMF. EMF stands for electromotive force. So the EMF of a cell is the sum of V plus V minus. V plus V minus. Okay, let's see what is V plus. V plus is potential. This is energy at the end of the day. This is potential of positive electrode relative to nearby electrolyte. And what is V minus? Potential of negative electrode relative to nearby electrolyte. Write this. Okay. Now have one concept before we go further. We have two chargers. One is a 2 ampere charger and one is a 3 ampere chargers, and these are the outputs of them. Fine. Okay. So let's say we have USB outputs. USB's standard output is always 5.1 volt. USB stands for Universal Serial Bus Controller. So the standard output is 5.1 volt. Have you understood? Right. So say suppose you have a cell phone and the cell phone is something like, say, it's a 1 ampere rated for charging, 1 ampere. You can coolly connect it to both. Always when you connect a device, first check the potential difference. Every cell phone needs only 5.1 volt. So you can coolly connect it to here also, here also. This one will be a fast charger for it. This one also will be fast. But its original charger is a 1 ampere charger. The 1 ampere charger, you will feel much more comfortable when you charge with. These are called power chargers. Right. Current is something that I draw. How much current will I draw? 1 ampere. I am designed to draw 1 ampere. How much it can deliver? Up to 2 amperes. How much it can deliver? Up to 3 amperes. This will happily charge it. Many people think then don't connect. Nothing like that. But if you actually have a 3 ampere phone and you are connecting it with this charger, it will take long time. And this charger will heat up. Because you are withdrawing more current. I square R. So example is very simple. As in grade 10 also I gave that example to you. And with that concept you will understand. what is like current is always drawn. This is a 2-burner gas stove at my home, right? And say my mom is making parathas and 2 of you have come to eat. Your eating rate will be maximum what? 1 paratha a minute, which is very fast. She can happily serve you 2 and keep discussing with you. Now, if 17 people come to my house, it's not that the quality of parathas will go down. My mom's temper will go up. Because by the time she has just served you, this fellow is asking paratha, this fellow is asking. Your withdrawal rate is very high. So you will see the frown on her face. Agreed or not? But say suppose you have gone to a Gurdwara where langar is being fed. At one stretch, they will be feeding how many people? 400, 500 batch. There, 17 children went to eat. Do they have any load? No load. They'll happily feed you. Is this understood? So current is something that you draw, and that's the reason you should be always connecting it to a source. For example, a car battery is 12 volts, and if I take that Duracell cell, this is how much? 1.5. So 1.5 means 8. So if I connect 8 of these also, I'm generating 12 volts in series. Got it? A Maruti 800 headlamp is a 55 watt headlamp which runs at 12 volt. It says if you connect it here, it will glow. If you connect it here, what will happen? Immediately all the batteries will exhaust. Because these batteries do not have a current withdrawal rate which is high. You have matched the voltage, but what about the current? It's 55 watt means its current withdrawal rate is very high. That's why in cameras and all we use batteries which are higher ampere. 2600 mAh. You say mAh. mAh means what is the capacity? What is the current handling capacity? Ampere hours, which say. So car batteries have got high ampere. They have around 35 ampere hours or 40 ampere hours, whereas these batteries are very small, so they cannot light up. But if you take your torch bulb and you connect it with the car battery, suppose that's a 12 volt bulb, and you connect it with the car battery, happily it will glow. It will not burst. Voltage is same. You have just asked a boy to go and eat in a 5-star hotel's kitchen. Every day you take your tiffin from there. They won't feel also that you have eaten something. Right? Chaliye. So let's now write about what is electromotive force? Electromotive force. So as I told you, electromotive force is the EMF, the maximum capacity. So we say it is the maximum PD, between terminals of a cell when no current is drawn. When no current is drawn, right? When no current is drawn. Why did I tell you that the Duracell cell EMF is not 1.5? When I bring a new Duracell, it is stamped 1.5, and I connect a multimeter, it's showing me 1.5. The multimeter is also a device which is pulling current. After pulling current, it is showing 1.5. That means the EMF must be more than 1.5. We don't stamp that because you will never get that output, and you will start complaining to me. Did you understand? Promise less, deliver more. If I say that the EMF of a Duracell single battery is 1.8, then you will come and connect it. You have to measure and get 1.8. So once you put an electrical device, an ammeter or whatever, or a voltmeter, current is running through it. So at that time, there is a drop. So EMF means, electromotive force means, take a cell and do not connect it to any device. What is the open terminal voltage? The open terminal voltage cannot be measured. The moment you measure, you are consuming some current. So when no current is there, it is known as to be the maximum PD. That is the EMF. Okay. So we say no current is drawn and the unit is volt. Although this is called force, this is basically energy, the form of energy. So let's see open circuit condition. Open circuit condition means the circuit, external circuit is not connected. So when no current flows, typically the one that I have shown on top, I is equal to 0, and we say no voltage is lost inside cell. Achha, what did I mean by no voltage is lost inside cell? Children, it is something like this. This is my cell. If I connect it to a circuit, suppose I have connected to a circuit, then what will happen? Current will be flowing. You agree or not? Once the current flows, there is something that he has to cross here. There's an internal barrier. So the internal resistance comes into play. Here we are saying open circuit condition. That means like this. Open circuit. Maybe you are having a circuit. We have a circuit out here. But after that, we have given a key and this is open now. Now no current is flowing. No current flows means there is no voltage loss. Voltage loss means there's a drop out here. There will be a drop. And this drop will always be equal to the current multiplied by the internal resistance. V is equal to IR. So the same concept. So in this case, we say the EMF is equal to the V. And V is known as terminal voltage. Terminal voltage equals the EMF. Fine. Go ahead. Okay. So number 5. Should I go back or what? You want me to go back? Tell me if you have not copied, I can go back. All okay. Internal resistance. So inside electrolyte, that's the same story that I told you. Ions move and collide. This is analogous to electrolyte offers a resistance. And this resistance is known as internal resistance. So the ions have to move through the electrolyte. They cannot move it so easily. So it's like electrolyte is responsible for collisions. Collisions are responsible for oppositions. Opposition for whom? For the movement or propagation of the charge carriers. And this gives rise to internal resistance. No real cell has zero internal resistance. There will be some internal resistance with everyone, denoted by small r. Okay. Now 6. Terminal voltage when current flows. Previous you saw when there was open circuit. At open circuit, E and V are same. Now here we will have internal resistance, which is equal to R. The current is equal to I. The PD drop inside cell will be equal to IR. Therefore, the terminal voltage will become E minus IR. So when you had an open circuit, I was equal to 0, V was equal to E. When you have a closed I flowing circuit, then I's value is greater than 0 and V becomes equals to E minus IR. Okay. Now, what did I tell you? If I connect the Maruti headlamp to those 9 batteries, what did I say? They will drain down the batteries very quickly because they want more current. So if you see here, if I is more, IR is also more. Got it? So V drops abruptly. And as a result, very quickly the cells will be exhausted. So we say more voltage loss in a cell. So please check the current always of the device. If the current demand is more, do not connect that device with your battery. Your battery will run down very quickly. Can I go ahead? Okay. So let's see our 7th point, current in the circuit now. Current in the circuit. So this is my circuit. A circuit basically has, imagine that there is one load and this load is the R. There's an internal resistance R here, the EMF is E, and I current is flowing through this circuit. Okay. And the terminal voltage is V. Children, are you able to comprehend this? E is this maximum capacity, R is the internal resistance, terminal voltage is V. I have connected to a circuit. The circuit actually has a resistance R. So Ohm's law tells me what? Ohm's law tells me V is equal to IR, and V is also equal to E minus IR. So I can write IR is equal to E minus IR. So IR plus IR is equal to E. So if you take I common, R plus R is equal to E, right? So the maximum current that you draw, this is also Ohm's law, V by I equal to R, I is equal to E by, isn't V by R equal to I is equal to V by R. So here we say that if you are getting V, if you use R, then you are getting terminal voltage. If you want to use EMF, then plug the entire resistance of the circuit. This is the total resistance of the circuit. And look, this R and this small r, are they not in series? Yes, they are in series. So what is their effective resistance? R plus R. R plus R is the net resistance. But in daily life, how we will calculate? We will not use this. We will use V by I equal to R. So we say I is equal to EMF divided by total circuit resistance. And how much is the total circuit resistance? This is always R plus R. See, it is something like this. If your mom says, go and get something, what is the total time for her to source it? Your mom always feels that the time taken for you to go to the shop and come back. No, you also will take some time to dress up and get ready before you go. Please add that time also, plus the time of travel. That is giving you the total circuit. Okay? Now we see maximum current. The maximum current. This is important. From a cell. How much current can I actually obtain from a cell? If external resistance R is equal to 0, then the maximum current Imax you can get is the EMF divided by R. Yes or no? This is the maximum current you can get. On this, let us also say something called short circuit. Short circuit. Short circuit means you are connecting one end of the cell to the other end. Short circuit, have you understood? Take one wire from one end of the battery and connect it to the other. Immediately it will heat up and it will cause even that one small 1.5 volt. So let's give you a small example. Say R is equal to 0.1 ohm, very small internal resistance, and the EMF is equal to 1.5 volt, comparable to a cell that you buy in the market, and you short circuit it. That is the maximum current. Let's see what is the maximum current. It is 1.5 divided by 0.1, which is 15 ampere. Very high current. So this is a high current. This can heat the battery and can also damage cell. In fact, if you do this, you will see a big spark coming up. Tak karke spark aa jayega. Fine so far. So let's summarize a bit between EMF and terminal voltage. I hope by now you understand. Terminal voltage is when you will be connecting a circuit. EMF is when it is in open circuit. This value will be more, this value will be less. So our first thing is, this is open circuit voltage. This is open circuit voltage, and this is voltage when current flows. This is maximum possible voltage. This is very ideal scenario. Maximum possible voltage, and in this case it will be usually smaller. Fine. This is independent of current because no current flows. Independent of current. This is dependent on current. Its value is E. Its value is E minus IR. For any distinguished type of question, you can use this. Just give me 5 more minutes. I just want to complete this section so that by the time we meet next time, it's only Kirchhoff's law. Done? Open circuit voltage, voltage when current flows, maximum possible voltage, this is usually smaller, independent of current, this is dependent on current, this is E, this is E minus IR. Okay? Now we will do combination of cells. Combinations of cells, and how do you combine and why you combine, when, what you should combine. Combinations of cells. They are pretty similar to combination of resistors or capacitors. So you must have seen in your remote control, if you see the reverse of your remote control, there will be 2 cells which are combined. So we can have one combination which is known as a series combination. Series combination. So always remember, a series combination is preferred where you want the voltage to go up. So what is a series combination like? This, like this. Current will always flow in one direction. Current always flows in one direction. Let's say this is E1, this is E2 with R1, and this is R2. Got it? What is the equivalent cell? Equivalent cell means if I am replacing it with one cell, don't you think that one cell should be E equivalent, should be equal to E1 plus E2, right? And it should also have a R equivalent, which is equal to R1 plus R2. Why? Because the 2 resistances are in series. Clear? So here we always say EMF adds. So you can write down equivalent cell, make this. Both cells push current in one direction. Both the cells will be pushing current in one direction. Both cells push current in one direction. But tell me children one thing. Tell me children one thing. If I see the current that I can obtain, okay, if I see the current, maximum current, the maximum current will be E equivalent divided by R equivalent. Do you get it or not? From this combination, that means it will be E1 plus E2 divided by R1 plus R2. Correct? But the day I introduce a circuit with it, another R will come up, the circuit's R will also come up. That means the current that I will be able to draw from it is less. Such sort of an arrangement is used only when current demand is less. Remote controls do not need very high current. And so we connect them in what manner? Series. Now see, this particular remote, if you see, you will say, no sir, it's not always like that. If you see this remote, it's a typical series combination. But in some AC remotes, you will see both the cells are together. But if they are together, then also it's a series combination. You will see always one cell will be like this, other cell will be like this, and a plate will be here on this side. It's basically a series combination. Just to reduce the space, they have connected in that manner. So when do we use series? We will use series when the voltage is our priority, current is not. So now comes a question. Suppose you want to design a power bank. In a power bank, voltage is not your priority. Current is priority. Power banks will never have cells in this manner. They will always have cells in parallel. Or say the inverter that I'm using. This is a single battery inverter. Suppose I want more backup. Backup hours need to be more backup hours. So there we don't use the word ampere, we use ampere hours. So many ampere for how many hours? So if you want to increase your backup, then you need more cells, not in series, in parallel. So is series understood? Okay. So if you now go by voltage, so let's say we put this as A point, B point, not B point. Let's say we put this point as B and we put this point as C. Okay. So if you see VAB, the voltage between, it should be E1 minus I R1, the voltage between these two. Correct? If you see VBC, it should be E2 minus I R2. This much. E2 minus I R2. Now if you want to see what is the voltage from A to C, we will add them. So it becomes E1 plus E2. Then minus of I R1 plus I R2. I could have better written it as E1 plus E2. Same thing I am doing. Minus I of R1 plus R2. I can write this as E equivalent minus I R equivalent. Finally, it becomes one cell. And through this also the current will be running, yes or no? So what is the drop now? The drop is now I R equivalent. And what is the EMF? E equivalent. Clear? So write down EMF adds and PD goes down. Fine. So we see parallel now. Parallel. Oh, sorry. Take it. Did you understand? It's the same thing. It's one cell whose EMF is now E equivalent, internal resistance is R equivalent. So the voltage you are going to get is V is equal to E equivalent minus I R equivalent. Now let's see parallel. All right. Now that we have done the series combination of cells, we will now be looking at parallel combinations of cells. So let's look at parallel combination of cells. So you will connect the cells in parallel in which the positives will connect with positives. So it's a very easy combination. So this is my first cell, okay, and this is my second cell. So I connect the positives together, I connect the negatives together, and let's say this combination of cells, this particular battery bank is driving an external circuit. Okay, this is driving an external circuit. Fine, this is parallel combination. So obviously the currents are going to come out from this. This is a cell with EMF E1, internal resistance R1. This is a cell with EMF E2, internal resistance R2. Right? Current drawn from this cell is I1, current drawn from this cell is I2. I1 and I2 merge together to give you I, and I current flows through the circuit. So that's I going from here, this is also I, and further they again bifurcate into I2 and I1. Perfect. Okay. And this circuit is actually now deriving a terminal voltage, say, of V. So we will now look at what is the equivalent. We'll have to look at what is the equivalent cell or the equivalent EMF of this combination, and what is the equivalent, what you call internal resistance. Now, when you had a series combination, if you remember, in series combination, your target was to get more voltage. Okay. So if you see a parallel combination, okay, a parallel combination, and this is nothing tough. If you use your grade 10 knowledge, that's sufficient. A parallel combination allows to draw more current. Here current is our significance. We will get more current from this combination, okay, and internal resistance, that is basically the equivalent internal resistance, is reduced. Obviously, if you want more current, the resistance has to be reduced. So when you talk about these things like, say, power banks and other, say, UPS backup, inverter backup, there we always go for parallel combination, because we want more current, we want more higher wattage devices to be run on them. So more current and reduce internal resistance. Now just apply your common sense. The resistances are actually connected in parallel. Since the cells are in parallel, the resistances are also in parallel, and we know in parallel resistance combination, overall resistance reduces. So if you just apply your common sense out here, what should be the effective internal resistance? It should be 1 upon R1 plus 1 upon R2. This is from grade 10, because R1 is an internal resistance, R2 is an, both are connected in parallel. So you can write 1 upon Req becomes equals to what? It becomes equals to R1, R2, and it becomes R1 plus R2. So from here we get that the equivalent resistance of internal resistance of cells connected in parallel is given by R1, R2 divided by R1 plus R2, and this equivalent will be less than either of R1 and R2. This is our grade, typically knowledge from grade 10 of what we had studied. Now we will see what is the equivalent EMF of this combination. So what I'm doing, I'm just reducing this portion, okay, and parking it aside. This is parked aside out here, and let's say what is the equivalent, what do you call, EMF. Now see, V is the ultimately potential difference. So V potential difference in a parallel network, if you have V out here, you should have V out here also, V out here also, because in a parallel network, it is current which gets distributed, voltage remains the same. So can I now write that V, if I consider this, I can write it as E1 minus IR1. The same concept. What is the terminal voltage obtained from a cell? It is the EMF of the cell minus the potential drop. And similarly, I can also write, it's I1. So I can also write V as E2 minus I2 R2, right? When I'm considering this one. From this particular equation, if I want to separate I1 R1, look, if I want to separate I1 R1, I get it as E1 minus V And further, if I want to separate only I1, I get E1 minus V divided by R1. Similarly, from this I'll get I2 R2 should be equal to E2 minus V, and if I separate I2, I get it as E2 minus V divided by R2. I hope this is clear. Okay. Now, applying the sum of currents I to be equal to I1 plus I2, right? I can write my I to be equal to E1 minus V by R1 plus E2 minus V by R2. Pretty simple, okay? I've just replaced I1 and I2 from what I have derived out here. So this can be now written as E1 plus E2, okay, divided by R1 R2 minus, if I take V common, it becomes 1 upon R1 plus 1 upon R2. Perfect. If I look here, so these are all the values of I is equal to R1 R2. Now this becomes E1 R2 plus E2 R1 minus V, and look how V becomes R1 R2 R1 plus R2, right? So we are trying to find out what? We are trying to find out the equivalent EMF of this combination. So we will separate V out, right? We will separate V out. So let's bring V this side. V into R1 plus R2 divided by R1 R2 is equal to E1 R2 plus E2 R1 divided by R1 R2. Fine. This finally gives me the value of V, which is the equivalent EMF. So V will be equal to the I comes here, it becomes E1 R2 plus E2 R1 divided by R1 R2, right? Divided by R1 R2 multiplied by, now this thing will be divided by this, so it will somersault. It becomes R1 R2 divided by R1 plus R2 minus I into, right? I into, it becomes R1 R2 divided by R1 plus R2. Now this is very interesting, right? So finally I write my V as E1 R2 plus E2 R1 divided by R1 plus R2 minus I R1 R2 divided by R1 plus R2. Now have a look. Just have a look at this expression properly, okay? Have a look at this expression properly. So this again tells you, if you see this component is the combination of the parallel combination of the internal resistance. This is the combination of the parallel, is the equivalent resistance for parallel resistance combination, and this is known as the weighted average EMF. So if you allow me to 1 minute, reduce, say, this part. I just don't want to change the screen, okay? If I reduce this part, then if I reduce this part, fine. How do I write this? I write that the equivalent EMF of parallel combination of cells is given by, okay, parallel combination of cells, or I write it like this. 1 minute, huh? I write that 1 minute. 1 minute. Okay. I can write this as the terminal voltage that I obtain, after making a parallel combination of two cells of EMF E1 and E2 with internal resistance R1 and R2 is a parallel combination. I get this. I replace this as E equivalent minus I R equivalent. Now recall, whenever you have a cell whose EMF is E, internal resistance is R, and you connect it across any circuit, okay, you connect it across any circuit, then the V that you get, the terminal voltage, is always E minus IR. So it is also obeying the same equation. Only thing is, this E is now the equivalent EMF, and for parallel combination we call this as weighted average EMF. Weighted average EMF. I hope now this becomes clear. So if I change the screen, okay, if I'm changing the screen, let's have a recap. When you do series, suppose you take E1 with internal resistance R1 and you take a cell E2 with internal resistance R2, then what is the terminal voltage you can expect? The two EMFs add up, E1 plus E2, and minus the drop. The drop will be R1 plus R2 because this is a series connection. And here we write it as V is equal to E equivalent, this is for series, minus I R equivalent, this is for series, in a better way, right? And if you see the same thing for, say, parallel, P-A-R-A-L-L, parallel, you have a cell E1 with internal resistance R1, a cell E2 EMF, internal resistance R2, then in this case we will say our V will be equal to, what happens in this case, E1, E2 don't add up, you get what is known as a weighted average. So the weighted average is E1 with the resistance of R2 plus E2 with the resistance of R1 divided by R1 plus R2 minus I into the potential drop, which is R1 R2 divided by R1 plus R2, right? If you see the same thing, R1 R2 divided by R1 plus R2, that means we say V is equal to E equivalent parallel minus I R equivalent for I. This is the story. So this will be honored. This shows that if you would have had one cell with an equivalent EMF of a combination of series, then this is what it is, equivalent combination of parallel. Fine. So let's wrap it up now and just put a comparison of both the type of cell combinations for certain parameters. So let's say we put series combination on this side, series combination, and on this side we put parallel combination. Parallel combination, right? And we compare them on parameters like, number one, comparing in terms of equivalent EMF. Comparing it on equivalent EMF. Here what happened? They add algebraically. So let's say that our cells, common for both, our cells are E1 with R1 and E2 with R2. So here equivalent EMF, which is E equivalent. So in this case, E equivalent will be equal to E1 plus E2. And in this case, we say it is weighted average EMF. So weighted average EMF means the E equivalent in this case becomes E1 R2 plus E2 R1 divided by R1 plus R2. Fine. Next point would be on internal resistance. So here also Req is equal to R1 plus R2, right? And here we will say Req is equal to R1 R2 divided by R1 plus R2. Fine. Our next combination will be on purpose, main purpose. main purpose. Here the purpose is to increase voltage. But children, remember, since your overall resistance is increasing, the current will drop down in this case. So this is a combination we usually use where voltage requirement is more and the current draw is not that high. Suppose like remote controls, cell or say torch lights, we always have it in series. Whereas here we will want more current withdrawal. This is typically battery banks, power backups, more current withdrawal. The internal resistance drops. Obviously, because in a parallel combination, that's why you in grade 10 also you learned that in parallel combination, you can draw more current because the overall circuit resistance drops. So the overall resistance drops down. So another thing that we can also see is that if we take identical cells, okay, let's say you're trying to build up a power bank, identical cells. So let's take say two identical cells which are having their, let's say we have two identical cells. So the other cell is E2, R2. Since they are identical, so these two must be equal, which is say E, and these two also should be equal, which is say R. Okay, so we have got two identical cells. This is the most what you call standard practice that we do in daily life. So we take two identical cells. Let's say this is a 1.5 volt cell, this is a 1.5 volt cell, internal resistance R, internal resistance R, right? And we are trying to do a series combination out here. So if you do a series combination, obviously the E equivalent that you will get will be an addition of both, right? So it will be 2E. Whereas if you see the R equivalent also becomes 2R. That means the R equivalent has shot up as compared to individual cells internal resistance. What I mean to say by this is each cell had an internal resistance of R, but the overall internal resistance has shot up. So you will not be able to draw much current from here. But if you do a parallel combination, okay, let's do a parallel combination. Then in the parallel combination, if I look at my E equivalent now, my E equivalent will be ER plus ER divided by R plus R, which gives you 2ER divided by 2R. So 2 cancel, R cancel, which is E. So if you have many 1.5 volts parallelly connected, your overall equivalent EMF will still be E. But the beauty comes here when you see the R equivalent. The R equivalent is R1, R2. Sorry, so R1, R2 this time will become RR divided by R plus R, which is R square upon 2R. So square takes away 1 of the R and your overall resistance is half R. So this is half the internal resistance of each cell. And this is the striking parameter due to which the circuit's resistance falls, and as a result of which you are able to draw more current. That's all. And in our next section, we will be dealing all about with Kirchhoff's law. So just practice this too, have a readout on this, and finally after that we will do problems. Okay, thanks then.